Assalamu alaikum, guys. Sorry for the delay. There was some sort of technical issue on my side. My PC went into some sort of update, and afterward, there were a lot of windows popping up and down. So couldn't been able to get hold of actually a couple of functions on the Google Class. So the I think the voice is loud and clear. Before I start and share the presentation, just write in the chat box that if it's loud and clear, so I'll start sharing the presentation. Okay, thank you very much. So today we're gonna most probably finishing up the infrared spectroscopy just to connect with what we discussed last time. If you remember that in the infrared spectroscopy, I said the basic concept is when the infrared radiation passes through the sample, a particular amount of that is going to be absorbed. And as a result of that absorbance, the molecules that absorb the light will either undergo a stretching sort of vibration and bending vibration. And we have gone through in detail that stretching vibration are of further two types, symmetric and asymmetric. And the bending vibration will be either in plane or out of plane. The in plane can be further as scissoring and rocking, while out of plane will be twisting and wagging. And we have seen these pictures to give you an idea about all these types. We also have discussed that the conditions or the criteria behind absorbance of the IR radiation is that when a specific infrared frequency is passed through the sample, the molecule will absorb only that particular frequency which will match with their internal vibration, and the rest of that is transmitted out. Only molecules gives IR absorption. The molecule must have a dipole moment in order to be used or in order to be applied for this IR spectroscopy. You all know about the dipole moment, that if there are two electro negative elements creating a partial negative and a partial positive charge. That's how a dipole moment is created. The mode of vibration should be in the, not be the center of the symmetry, and the molecules should be polar. It's the same thing as I said, having a dipole moment or a polar molecule. And we have gone through these types of mode of the molecule, where I said that we are not interested much in the mathematics, but just to let you know that the mode of the vibration as a result of absorbance of the specific infrared radiation would be translation, rotation, and vibration. So today we're gonna start from what is IR spectrum. If you remember last time, we discussed with the diagram that when a specific light is coming from a source, how it's going to split up and then reunite and then pass through the sample. Once it passed through the sample, depending upon what sort of molecules are there in the sample, a particular amount of the light, as I said, is going to be absorbed, which results in, those kind of modification we just discussed. And the rest of the light is going to be transmitted out. Now, the light which is coming out as transmittance will then be fall onto the detector, and the detector is connected with the software with the computer, and that is going to give you a chart which is called the spectrum or IR spectrum. And that IR spectrum is actually your tool by which you're going to determine much about the molecule of interest, like what sort of information you actually wanted about that molecule. So here is the picture of an IR spectrum, a typical IR spectrum that comes out as a result of the passing of the infrared radiation through the sample. Now, very important point to be mentioned here, that IR spectrum is actually the graphical representation or a graphical plot of the transmittance versus the vibrational frequency or the wave number. Now, previously, what we have been doing in the visible spectroscopy, if you remember, we were mainly interested in the OD or the absorbance. But here, the thing that we're going to be measuring is not the absorbance. The thing that we're going to be measuring is the transmittance. So the IR spectrum is actually between the percent transmittance and the wave number, right? So we know that according to the law, the frequency is inversely proportional to the wavelength, and the transmittance is actually intensity of the transmitted light versus or divided by intensity of the incident light. So it is to be understood that the intensity of the incident light would be more, because after that some amount is going to be absorbed and the rest is going to be transmitted out. So this is how we calculate the transmittance, and this is how we calculate the wave number, and by keeping these two in mind we can plot a graph to get the IR spectrum. Actually we are not preparing the graph because it's all automated. We know the machine is going to prepare the IR spectrum for us, but you should be aware of the fact that IR spectrum is actually a graphical illustration, which is a relationship between the percent transmittance and the wave number. Now, the IR spectrum is being divided into two types based on, again, the type of the molecule we are interested in, what sort of information we wanted about that molecule, and what sort of infrared radiations we are using. So the first IR spectrum is specifically for the determination of the functional group region. Like whatever molecule of interest you have, it might have a functional group, might be a carboxylate group or a methyl group or any other functional group. So if you are particularly talking about the IR spectrum of a functional group region of any molecule, the wave number or the frequency will be ranging in between 4000 to 1500. While for another type of the IR spectrum, which is called the fingerprint region, what is fingerprint region? A fingerprint region is a kind of IR spectroscopy where we'll be identifying the exact molecule in terms of its changing or bending vibration. So in one case, we are interested in only knowing the exact change that takes place in a molecule as a result of this IR spectroscopy. And in another case, we are interested in knowing the functional group. So for this fingerprint region, it's between 1500 to 500 in terms of the wave number. So as I said that for the functional group region, you can see here, it identifies the functional group of the molecule with the consequence of changing the vibration. Now the concept remains the same, because as a result, when the IR light passes through the molecule, as I said, it absorbs the light. And as a result of that absorbance, you know that it either undergo stretching or bending depending upon what sort of molecule it is. So actually in the functional group region, it identifies the functional group with the consequence of changing the stretching vibration. Only stretching mode of vibration is applicable in this. So this region contains few peaks. The pattern of the peaks is easy to analyze because stretching vary within a narrow range. So you can see here, this is what we call the functional group region, where you can see very few peaks are there, and it's easily identifiable because they are separated from one another. While in case of the fingerprint region, which is in this range, it identifies the exact molecule, as I said, with the consequence of changing the bending vibration. So the basic difference here, that here we are talking about the stretching vibration, and here we are talking about the bending vibration. Now, stretching and bending both are occurred in this case as well, but bending is more than stretching when it comes to fingerprint. The pattern of the peak is more complicated due to the complex vibration which create a unique IR band to distinguish compounds. So you can see that this is a bit of the more complicated side, where we say that this is called the fingerprint region. So Now the point is clear that IR spectrum is a graphical representation which is being made between percent transmittance versus wave number. And we have divided the IR spectrum into two regions, a functional group region and a fingerprint region. And we have gone through their specific role, that what we are interested in print region and what we are looking at for the functional group region. So at the end, we can say that the functional group region, it's sharp, broad, strong, and the medium peaks. While in case of the fingerprint region, they are sharp, but they are weak peaks. Now, here are some examples to further elaborate what actually I was talking about. As I said that in case if it's a peak of a functional group, so it may be either depending upon the shape or it depends on the intensity. For example, if this is the molecule where we have, the functional group attached here and here. So you can see that either the peak of the functional group is based on the intensity, which refers to the height of the peak, or it depends on the shape, which affects or which depends on the width. So you can see that this is what we call the height of the peak, right? And this is what we call the width of the peak. So the very important point is that the peak length or the height is actually referring to the intensity of the functional group, while the width of the peak is actually referred to the shape of the functional group. So in that case, it can be either broad or it can be either sharp. Like in this case, you can see it's broad. In this case, it's sharp. The width is more here as compared to this one. So if it's a broad, it might be due to the hydrogen bonding or presence of water molecule. It's one example. Now, in case if you're talking about the intensity or the height of the peak, it can be divided into strong, medium, and weak. A strong peak is a one that covers most of the y-axis, just like this one. This is called a strong peak. You can see that's almost going down the axis. A medium peak is the one that falls to about half of the axis. Maybe you can call this one as a medium peak. And a weak band falls about 1/3 or less of the axis, might be this one. So the peak that we are getting on the IR spectrum, specifically I'm talking about the functional group peak, they may be sharp, which is based on the structure, and they may be talking about the height or the intensity, which refers to the amount itself. And then they can be further divided into broad and sharp, and they can be of strong, medium, and weak intensities. So the factors affecting the peak intensity specifically are electromagnetic difference. That means the polarity. So more the polarity, more the dipole moment, more the dipole moment, more intense peak will be observed. Here are some more examples about how different factors affect the vibrational frequency of different functional groups. So again, we are not going in much of the detail, but just wanted to let you know the relationship, how different factors are related to have their effects on the vibrational frequency of a particular functional group. Let me start with the first one. Effect of different mode of vibration is directly proportional to the frequency of stretching. So that means different modes of vibration will have frequencies of stretching which is higher than the bending mode of vibration. Similarly, reduced mass of atom is inversely proportional to vibrational frequency. That means if you have more atomic mass, you have more vibrational frequency. Then we have more vibrational frequency results in the more force. Similarly, electronic effects, which I just mentioned above regarding dipole moment or resonating structure, just like we have got in benzene, or conjugation where we have alternate single and double bond, they might have impact on the vibrational frequency. And we see that these electronic effects have a direct proportionality with the vibrational frequency. Similarly, hydrogen bonding will also affect the vibrational frequency, and it shows here it's inversely proportional to that. Multiplicity of the bond, that means the number of the bond, they are also directly proportional to vibrational frequency. And then nature of hybridization, you know about the carbon hybridization structures. So percentage of S character is directly proportional to bond strength, and bond strength is inversely proportional to bond length. Or if we omit this out, we can say directly that bond strength is directly proportional to the vibrational frequency. Or you can say simply the S character is directly proportional to the frequency. And what is S character? This is the nature of hybridization. If you recall the hybridization model that you have studied about the benzene, you know SS overlap. That's what I'm talking about. So let me quickly summarize that the factors affecting the vibrational frequency. Why we are talking about vibrational frequency? Because vibrational frequency is the foundation of IR spectroscopy. So the factors affecting vibration frequency will definitely affect the IR spectrum. So in summary or in short, reduced mass of atom is inversely proportional to vibration frequency. Electronic effects like conjugation or resonance are directly proportional to vibrational frequency. Hydrogen bonding is inversely proportional. Then multiplicity of the bond is directly proportional, and nature of the hybridization is directly proportional to the vibrational frequency. Now, here is another picture of a graph where we'll be looking at the method to do the interpretation of the spectra, because as we have seen this picture here, we have seen a lot of peaks. We can see that few of the peaks have a more width. That means, as I said, it's about the structure. Then we have more intense peaks. We have more complicated peaks here as compared to this. We know that this is what we call the fingerprint region, and this is called the function group region. But the more important part is that how we're gonna interpret these graphs, because that's what the most important part is. Why we are doing this IR spectroscopy, that in order to get that IR spectra, and based on that we will analyze the data and we'll do the interpretation. So in generally, IR spectra isn't generally used to determine the whole structure of an unknown molecule, but IR spectra is great for identifying certain specific groups. Why? The reason is that this technique is very, I would say, specific, and it has got a high level of sensitivity because of the fact that it is a more sensitive technique. Then in this case we generally do not use the IR just to determine the whole molecular structure. Rather, we will be using the IR spectra or this technique specifically to identify or get an idea about specific particular atom or group of atoms within the molecule. So that's why I said it's more specific technique in order to be used, not for the whole determination of the structure. Now, in an overview of the IR window, which is ranging from 4000 to 500 in terms of the wave number, we have various region of interest which are highlighted. Now, you can see, again, it's not that important to remember, but there are few informations there which can give you the idea. Like, for example, this region, which is of 1650 to 1800, is of carbonyl group. So if a peak is coming in this region, the peak intensity and the peak width is going to give you information about the carbonyl one. Similarly, this from 500 to 1000 is the region which we call the fingerprint region. And as I said, that this is specifically used for the generality, not for a specific purpose. Then this one region between 2100 to 2260 is specifically for carbon nitrogen triple bond structure, or carbon carbon, that is the alkaline functional group. Then we have this one which refers to carbon hydrogen. This refers to the OH stretch. This region refers to the alkyne, and this region refers to the nitrogen and hydrogen bond. So you can say there are different functional groups being shown here, and you can see that all of these different functional groups, the important part is that the peaks that we are getting would have different intensities, and they have different widths depending upon the functional group we are talking about. So that means if we have the understanding about these functional group, which we have, so when we got the peaks, we can identify the peaks very easily depending upon which region they are coming in, and in terms of their width, in terms of their intensity, we can identify about these different functional groups. So basically 80% of the most useful information for our purpose can be obtained by looking at specifically this region, which one this is, right? And a specific area of spectrum. Remaining forest of the peak from remaining peak from 5 to 1400 is a fingerprint version, which is comparatively less useful. So because of the nature, as I mentioned earlier, this complicated nature where the peaks are so close and joined together and kind of overlap, so it's very difficult to do the analysis in this region. That's why we are saying that we are not pretty much interested in that region of fingerprint. Rather, we are interested in this region where we have got separated peaks, well defined, well identifiable, and that is the most important part of the IR spectrum. Then this is another some information about different zones and the functional group that we normally identify. Zone one is of this wave number. Common symbol of the bond is XH, which include OH, CH, and NH. Then the zone 2 lies in this region, and the common symbol is X triple X, that means triple bond. So it could be a carbon nitrogen triple bond or a carbon carbon triple bond. Then similarly, this one is a double bond, and it could be a same atom double bond or a different atom double bond, which is in CO case. And this one, which is either a CO bond or a CC bond. So these are the four regions. They are their wave numbers, and these are the common symbols of the group that we identify. So based on that, if you look at the zone 1, the example of that is OH. So OH bond stretching is lying between this region with strong intensity and broad U elongated shape. So you can see here, the diagram is very, very small, but if you just look at it and afterward the class you can go through in detail again, this particular peak here is referring to OH because of the region where it is falling, intensity, and the width. Similarly, another example is of terminal alkynes, which have a carbon hydrogen single bond stretching in this range with a stronger and a sharper peak. So, in case the OH has got a strong intensity but a broad shaped peak, while that of the carbon hydrogen bond would have a stronger and a sharper peak. So, if they both are lying in the same region as they are somewhere, but based on the shape, you can identify this peak with this kind of peak, right? So that's how you identify if you've got two peaks coming in this region of zone 1. The OH peak is a bit of wider, while in case of the CH peak is bit of a sharper peak with a stronger intensity. So that's how you identify. This is one example. Then these are a few more examples, and you can go through this, like for the other NH bond, and then for the other examples, how to differentiate different peaks coming in the same region depending upon their intensities and depending upon their widths. Similarly, in zone 2, we have carbon-carbon triple bond and carbon-nitrogen triple bond. Somewhere you can see they are overlapping in terms of the region, but they also have a variable intense and sharp peak, and they also have some variable intense and sharp peak. So if you identify here, you can see that this one is the carbon-carbon peak. This one is also referring to a carbon-carbon peak, while this one here is referring to carbon nitrogen peak. So this is, it's not easy. Like, you need to have understanding of the whole reading of this IR spectra, and that comes with the practice. When you do a lot of practice, then you came to know, and you have understanding of the standard where actually you will be expecting the peak, because whenever you perform the experiment, you run with the control, and the control is the what so you can compare the peak with your control as well. Similarly, for zone 3, this is one example of carbon oxygen bond where you can see the peak will be lying in this region. It will be something like this, and the regions for the ketones, for the carboxylic acid, all functional group would have different region. Why we are talking about all these functional group here? Because the common thing in all of these functional group, is the carbonyl group, but they have differences in terms of their functional group, so they have differences in their peaks as well. Similarly, example of carbon-carbon bond here is being shown. Then for the zone 4, you have carbon-carbon single and carbon-oxygen single bond. Then they have, peaks ranging in this range, and you can see the difference of carbon-oxygen bond here. You can see this one, carbon-oxygen, and this one is carbon-carbon. So these all have very much specific locations in terms of their wave number, specific shape, where you can identify and cross-examine about the functional group. So finally, we're going to end up with a few of the applications of IR spectroscopy. As we have gone through the lecture, we identified that IR spectroscopy can be used to identify an organic compound, for structural determination, for identification of the functional group, uh, also to study the progress of the reaction, because as the reaction is progressing, the structure is changing. So that is also one part of application. Distinction between two types of hydrogen bond, study of the keto-enol tautomerization, that one form of the isomer is converted into another form, and that's how you see how this change is going place. Study of cis-trans isomerization, which is another conformational change, conformational analysis of different other types, determination of impurities in the compound can also be one application, and presence of water sample is another application of this one. However, there are certain limitations of the IR spectroscopy as well, and we know that every technique would have limitation and application. So in terms of the limitation, it cannot determine the molecular weight of the compound. Now, for this, you have other techniques like mass spec and others. Doesn't give information about relative position of different functional groups. From the single IR spectrum of an unknown substance, it is not possible to know whether it is a pure compound or a mixture of compound. Like for the purity, you go for HPLC and all other type of the techniques. Sample cells are made of halogen salts, which are susceptible to moisture. So if the water gets into, it interferes, as you see with the spectroscopy. Gas samples can't be handled as the lack of sensitivity. So these are, like for the gas samples, we have, gas spectroscopy and different other HPLCs are being used for that. So these are the limitations for IR spectroscopy. So with this, we have finished the presentation, and with that, we have completed the course content of discussing about ultraviolet and infrared spectroscopy. So if you have any question at this stage, you can raise your hand and ask the question. Otherwise, you can go back and read the presentation again and can come back anytime for any questions. So the forum is open for the question. If you have any question, just raise your hand, please. Okay, if no question at this stage, that's fine. Just go through the presentation again. And as I said, you can come back anytime if you have any questions, and I'll be more than happy to give you the answers for that. Thank you very much for this. And with this, we complete our part. And inshallah, looking forward to teach you guys in some other courses in the near future. Thank you very much, and Khuda Hafiz.